Good afternoon, students. Myself Dr.S.Manikandan, Professor, EC Department, P.S.R Engineering College. Today class, we want to discuss about digital IIR filter design. Here I consider for that Butterworth approximation and low pass filter design. First of all, the magnitude response of Butterworth approximation is the filter design they give for the magnitude response with respect to digital frequencies. In IIR filter design, we can't directly design a digital filter. First of all, we design an analog filter, then we can map into that digital domain. In this case, the filter design is happen in Laplace S domain, then it will be mapped into that Z domain, that is a digital domain. Here, but the problem is given in digital domain specifications. Okay. Here, this is the magnitude response of Butterworth approximation. In this Butterworth approximation filter has some properties, right? The Butterworth filters are all pole design, means the zeros of the filter exist only for at infinity. Okay, the filter is order n. The filter order n is completely specify that the IIR filter, and the magnitude response of IIR filter is approach to that ideal response when the n is increases. Then another point is the magnitude is maximally flat at origin. Then the magnitude is monotonously decrease when the frequency is increased. That is the information related with Butterworth approximation. Here the two amplitudes we can consider. One is called as the gain at passband edge frequency, which is specified in this problem. The another one is called as A2. A2 is called gain at stop band edge frequency. The edge frequency, namely it called as omega 1 for passband, stop band it is called as omega 2. These four parameters is very important for design of a filter. The first step is choose the transform. Here first we design an analog filter. That analog filter is transformed into digital domain. In this case, two type of transforms is used. One is called as bilinear transform, another one is called as impulse invariant transform. The first step is you can choose the any one transform. For example, bilinear transform means bilinear transformation may be used here, means the analog frequency and digital frequency relationship is expressed as ohm 1, that is equal to 2 by T tan of omega 1 by 2. Same way, the another edge frequency is omega 2. From this digital frequency we can calculate for analog frequency, which is equal to 2 by T tan of omega 2 by 2. The first step, it have two different transform which is used for the mapping of the frequencies. The another transform is impulse invariant transform. In this case, the analog frequency equal to digital frequency divided by T. The T is called as sampling period. Same way, and ohm 2 that is equal to omega 2 by T. Okay. Then the second step of the design is we can find for the ratio of between ratio of analog frequencies, that is ohm 2 by ohm 1. Okay. In this case, bilinear transform means we can take this ohm 2 divided by ohm 1 that is equal to tan of omega 2 by 2 divided by tan of omega 1 by 2. Okay. Because of the 2 by t is numerator denominator same, it is cancelled. The another transform is impulse invariant transform, means here ohm 2 divided by ohm 1 that is equal to omega 2 divided by omega 1. Okay. The third step of the design is decide the order of the filter. Okay. The order of the filter is determined by a equation of n greater than or equal to 1 by 2 log of 1 by A2 square. A2 means here it is the gain at stop band, minus 1 divided by 1 by A1 square is a gain at pass band, 1 by A1 square minus 1, okay, divided by log of ohm 2 divided by ohm 1. This is the equation. Here the n is integer, so you can choose a value is equal. This is integer means you can take the same value. Suppose it is in binary, for example 2.3 means you can consider a greater integer value of 3. You assume that n is equal to 3. Right. Then the step 4 is finding this. This is for step 3. Step 4 is finding cutoff frequency of the filter, low pass filter. The cutoff frequency of the low pass filter is expressed as ohm C that is equal to ohm 1. This is a pass band H frequency in analog divided by 1 by A1 square, means gain at pass band minus 1, the power is 1 by 2n. N is the order of the filter. Okay. Suppose you can consider here as a bilinear transform, means ohm C that is equal to 2 by t tan of omega 1 by 2 divided by 1 by A1 square minus 1 power 1 by 2n. It is an impulse invariant transform technique, means the ohm C that is equal to omega 1 divided by 1 by A1 square minus 1 power 1 by 2n. Okay. Next steps, we want to move for determine this transfer function. HAFS is called as analog transfer function, analog filter transfer function. Here the n is even. Unity DC gain filter is expressed as HA of S that is equal to pi. The case varies to 1 to n by 2 ohm C square divided by S square plus BK ohm C into S plus ohm C square. Maybe this NS add. The HA of S is expressed as pi ohm C divided by S plus ohm C pi k is equal to 1 to n minus 1 by 2 ohm C square divided by S square plus bk ohm C S plus ohm C square. Okay. Here the bk is a coefficient. The bk is expressed as 2 into sine 2k power 2k minus 1 divided by 2n into pi. Okay. First, we design an analog filter, then the analog filter is transformed into a digital filter. Okay. Let's now we want to design a filter, digital filter, using the following specifications. Okay. Let us consider here design a Butterworth digital filter using bilinear transform. We can consider here bilinear transform for the design, and the specifications are given as 0.9 less than or equal to mod of h omega less than or equal to 1 when the omega is lies in between 0 to pi by 2. The another specification is mod of h of omega is less than or equal to 0.2. The omega is varies from 3 pi by 2 to pi. These are the specifications is given in this problem. From this, the specifications, the A1 is here the passband amplitude gain A1 is 0.9. The corresponding H frequency is omega 1, which is equal to pi by 2. Okay. The another gain at stop band H frequency is 0.2. The frequency, corresponding frequency is 3 pi by 2. These are the 4 specifications given. We can use these 4 specifications. We can design a filter. Okay. The first is we can design the filter. The first step is first you can find for analog frequency from this digital frequency. Here the consideration is bilinear transform, so you can apply for this formulas, right? Here the omega 1 is pi by 2, so you can substitute here pi by 2. Okay, you can get t also is given. T is assume as 1. Suppose it's given, you can take it. Otherwise, you can assume t is equal to 1 second. So from this equation we can get finally 2 into tan of pi by 4. The result is 2. Tan pi by 4 is equal to 1. We can get 2. Same way you can get this for ohm 2 t is equal to 1. So 2 tan omega 2 is 3 pi by 2 divided by 3 pi by in this problem it is specified 3 pi by 4. Sorry, this 4. So you can take this 4 divided by 2. You can get 2 into tan of 3 pi by 8, which is equal to 4.828. Okay. Then you can find for the ratio metric, right? Here the second step is you find this ratio metric of this analog frequency ohm 2 by ohm 1. Ohm 2 is here 4.828 divided by 2. You can get 2.414. Am I right? The next step is we want to find for the order of the filter. Just you can apply this, substitute the values A1 is equal to 0.9 and A2 is equal to 0.2. You can get finally, you can substitute here, it is a 0.2 square. Here it is a 0.9 square. Okay, it is 0.9 square. This value is already we can get it. This is 2.414. Now we can substitute. Finally, you can get n is greater than or equal to 2.626. Okay, but the n is integer, so we can take or choose n is equal to 3. Now the order of the filter is 3. So here it is represented as 3. N is equal to 3. You can get 1 by 6, and you can substitute the Ohm value also 2. Look at here 2. You can substitute here 2, and A1 is 0.9. So 0.9 square. Finally, you can get Ohm C is equal to 2.5467. Okay. The fourth step. The fifth step is we want to design for a transfer function of analog filter. Okay. Here n is 3. So n is add means you can take this equation. So the H of s is Ohm C value is 5467 divided by s plus 2.5467. Then here n is equal to 3. So substitute here n minus 1 is 2. 2 by 2 1. Okay. This equation also is present here. So 2.5467 squared divided by s squared plus b1 Ohm C. Ohm C value is 2.5467 into s plus 2.5467 whole square. Okay. Fine. Now we want to find for the value of b1. The b1 is equal to 2 sine 2k minus 1 into pi divided by 2n. Here k is 1. Only one coefficient. So k is 1. Substitute sine pi 2 minus 1 1 into pi 2, the 3, n is 3, so pi by 6. So we can get this here, it is 1. Okay. Finally, we can get a transfer function is H of s. HA of s means this is analog filter, which is equal to 2.5467 divided by s plus 2.5467 multiplied by 2.5467 whole square divided by s square plus here the b1 value is 1, so you can get 2.5467 s plus 2.5467 whole square. Okay. Once we have designed this analog filter, this filter should be transformed into digital domain. The same transform should be considered. In the bilinear transform, the digital filter H of z is determined from this analog filter of HA of s. The s should be replaced by 2 by t, which is multiplied by 1 minus z power minus 1 divided by 1 plus z power minus 1. Okay. Already the t value is 1, so you can get here it is a 2. In this equation, you can substitute s equal to 2 into 1 minus z power minus 1 divided by 1 plus z power minus 1. Finally, we can get a H of z equal to 0.23321 plus z power minus 1 cube divided by 1 plus 0.439 z power minus 1 plus 0.384 z power minus 2 plus 0.041 z power minus 3. Okay. From the specifications, the first we can determine this analog frequencies, and you can calculate the ratiometric of analog frequencies, then determine this filter order n. Here the filter order is n is equal to 3, right? It is reflect that the digital filter, the order is 3. Okay. Thank you.